Thank you so much for the introduction. Thank you so much for the invitation. I'd like to report on a number of papers joined with these people, everything over the complex numbers. And I'd like to start with a cliffhanger. However, I fear that some of you have seen this cliffhanger already, so let me just call it a teaser. So, as a motivating example or motivating problem, let me formulate the following theorem. X minimal projective of general type. And by this I mean it has terminal singularities kx is naf. And then we have an equality of Miyaoka-Yau type on that singular space, namely 2 times n plus 1 times second Chern class of the tangent sheaf minus n times first Chern class of the tangent sheaf square times canonical class to the n minus 2 is larger than or equals to 0, where n is, of course, the dimension. And in case of equality, x is a singular Borel quotient. This theorem has, of course, a long history. For manifolds, this is a classical result, I think, due to Yau. For singular spaces, it was announced several times, but to the best of our knowledge, no result has appeared so far. Right, and I'd like to explain how Simpson's approach to the uniformisation problem via the Nonabelian Hodge correspondence actually does work in that singular setting, and what results can be expected there. So first, maybe a few remarks are in order. One remark is the terminal implies x is smooth in codimension 2. So the singular set is of codimension 3, which means that first and second Chern class make sense. So I don't have to discuss anything scary here. So C1 and C2 makes sense. Maybe a second remark is that this theorem is meant to be an amuse-bouche. Really, if you're willing to use more elaborate words, then we have a full characterization of singular Borel quotients in that sense. And the results have meanwhile been expanded by Tarji-Rousseau, Tarji-Genancia to cover a large number of other cases. X need not be minimal, and then you talk about fixed part and non-fixed parts. Or X need not be of general type, just positive codiral dimension, or there's a boundary divisor. So there's a number of cases where related things can be said. Maybe, however, I should say what I mean by a singular Borel quotient. So this is proposition and definition. So X normal compact, then the following are equivalent, namely X is of the form unit Borel modulo gamma, where gamma in the automorphism of the unit Borel. So this is discrete and acts freely in codimension 1. or secondly, X is of the form y times gamma, whereby y is a classical Borel quotient. So where y is a smooth Borel quotient. So in particular, one of the points I would like to make here is as a side remark or trivial corollary, this is an example where Chern class conditions enforce quotient singularities on a space that has terminal singularities, so a priori need not be quotient. No. This is like infinite finite. Yep. Right. So as I pointed out, what I would like to do really today is to give an overview how Simpson's theory can be made to work in this context. However, maybe it's not as widely known as it should be, so let me spend a few minutes to say a word about the classical Corlett-Simpson Nonabelian Hodge correspondence here. So the Nonabelian Hodge correspondence. So, and the main theorem, which is Corlett-Simpson, is the following: X smooth, projective, then we have an equivalence of categories between, on the one side, or maybe projective H so between Higgs bundles on X that are H semi-stable and first and second Chern class vanish. This is the category on the one side, and on the other side there's locus systems. This is an amazing result about which many things can be said. I could probably spend a semester, or I rather would refer that semester to Essay. Let me just point out the basic definitions and one or two of the basic facts here. So most importantly, I should say what is a Higgs bundle. So what is a Higgs bundle? And a Higgs bundle is a locally free sheaf E, so equipped with an OX linear morphism from E goes to E tensor omega 1x, usually called theta, also called the Higgs field, such that the induced map theta, which goes from E to E tensor omega 2x, vanishes. So if you look at the definition of theta, this might look like a connection, but it's not a connection, it's OX linear. Right, and there's nothing more to it. So for instance, take theta equals 0 and you have a Higgs bundle for any locally free. Then I should probably say what is a sub-bundle of a Higgs bundle. So a sub-bundle F in E is Higgs invariant if theta von F, which in principle is in E tensor omega 1x, happens to end up in F tensor omega 1x. And a morphism of Higgs bundles, I'm talking about categories here, is what you think it should be. So a morphism is, so you have your one Higgs bundle F, you have a Higgs bundle E. When do you call this a morphism? Of course, here you have the Higgs field. Here you have the Higgs field. And you want this to be a commutative diagram. So this is all there is to it. And then I'm using the word semi-stability. Semi-stability here refers to slope semi-stability. Slope is measured with respect to h. However, you don't look at all subsheaves or subbundles, you only look at Higgs invariant subbundles. So so semi-stability refers to slope. So looking at Higgs invariance only. Right. And this is all there is. Right. Maybe I should give one example which will be relevant further. Bitte? Sorry?
What is written? Looking more at Higgs invariant.
Yeah, Higgs invariant subbundles. Higgs invariant is defined here for a subbundle. All right, so one example. One example is, E is omega 1x plus OX. This is a terribly important example. And the Higgs field, theta, goes from omega 1x plus OX to omega 1x plus OX tensor omega 1x. And I should say what it is, namely A plus B goes to 0 plus 1 tensor A. And you have to check that this actually is a Higgs bundle, and if you're bored with my talk, you might want to work out what the Higgs invariant subbundles are in this case. Right, and whether for your favorite example of a projective manifold this is stable or not. Okay, so maybe one further example, which is also a terribly important result in this direction. So, example. So, consider a polarized. Pardon?
The one here doesn't seem to be right. I mean, it's not linear, is it?
This is linear.
A plus B
goes to 0 times A. That makes it linear.
Tensor A, okay.
Tensor A, yeah. So consider a complex polarized variations of Hodge structure on your X, and then you get a local system via the Gauss-Manin connection. So Gauss-Manin, so gives local system. So then I apply the Colette-Simpson correspondence. That means I get a Higgs sheaf or a Higgs bundle. So get a Higgs bundle. And one cornerstone of the whole theory is that these bundles that appear in this way are characterized. So fact is bundles, such Higgs bundles are precisely those that where such Higgs bundles, say, E theta are precisely those where E theta is isomorphic as a Higgs bundle. We have discussed morphisms of Higgs bundles, so we know what isomorphic means. E comma lambda times theta for all lambda in C star. So this is actually a way when you have a Higgs bundle, you can get a new Higgs bundle by just multiplying the Higgs field by 12. That will stay a Higgs field, and the resulting new Higgs bundle might or might not be isomorphic to the old Higgs bundle if you take this for a definition of morphism. And one of the central insights of the whole theory is that Higgs bundles that are C star invariant, so scaling gives you a C star action on the moduli space of semi-stable Higgs bundles. Higgs bundles that are C star invariant are precisely those that come from variations of Hodge structures. And Simpson's approach to the uniformisation problem is find on your given manifold a Higgs bundle which by construction will be C star invariant. So for instance, this might be a good candidate, which by construction will be C star invariant. So almost for free, you get a variation of Hodge structures. And then the uniformisation problem is attacked by looking at the period map of this variation of Hodge structures. And if you devise your Higgs bundle in a clever way, then you can guarantee that you get uniformisation by the unit ball. This is his idea, and we have nothing to contribute in this direction. So instead, I would like to talk about Higgs sheaves on singular spaces. So what should a Higgs sheaf on a singular space even be? And for us, this is, personally, I can't speak for my co-author, but for me personally, this is, if you wish, our main contribution. We think we found the right definition. The definition is very delicate, and as you will see in a second, comes with a great many problems, but we still think it's the correct one. So, definition, X non-normal, a Higgs sheaf is a coherent E and an OX linear morphism theta from E into E tensor omega 1x double dual, and I will frequently write omega 1x with square brackets for this. This might look harmless, but it is interesting. So this, we think, is the definition of a Higgs sheaf. What's good about it? So, positive aspects. If you're interested in birational geometry, then you might be interested in the category, if you wish, of KLT spaces. Oh, yeah, such that theta wedge theta equals 0. Thank you. So if, I don't know, phi from x to y is morphisms of KLT, then I have a pullback map of sections in omega 1 double dual. So that goes from phi pullback omega 1 y to omega 1x. This is maybe more interesting than it looks like. For instance, you might have morphisms that end up in the singular locus of y. And then a section in the double dual is the same as a section that's defined on the smooth locus of y. Yet it defines something on the singular locus. But then using this means that you get, if you have a Higgs sheaf on Y, you get a Higgs sheaf on X. So we have pullback of Higgs sheaves. If X smooth, I get a Higgs field on not only the pullback, but also on the pullback double dual. So this is definitely something interesting. With this definition, you have functorial pullback of Higgs sheaves. So what is bad about this definition is so negative aspects is if F is a subsheaf of your Higgs sheaf, then you have F tensor omega 1x, you have E tensor omega 1x. You get a morphism, but this is not injective. None of these two sheaves is locally free. Even if they're both reflexive, the tensor product might have as much torsion as you like, and there's a morphism here, but it need not be injective. So bottom line is, it makes no sense to talk about subsheaves or subobjects, or even morphisms, unless some of the sheaves in question are locally free. So with this definition, the Higgs sheaves do not even form an abelian category. So then what do I even mean by stable? So I define, so is not injective, so define stability or semi-stability by looking at subsheaves that are Higgs invariant on X-rag only. So, and as you clearly guessed, that leads into all sorts of technical difficulties. There's another catch here that I don't want to dwell on, but I said you can define a Higgs field on the pullback of your sheaf and then the reflexive hull of this. This is extremely useful. However, taking the reflexive hull is notoriously ill-behaved with respect to pullback, which is tensor product. So you get a notion of pullback, but this pullback that you define in this way is not functorial in morphisms. So pullback via a composition of morphisms is not the same as pulling back once and then again. So this is maybe not so good looking. But I still claim it makes sense. So what we can do with this theory, using all the technology that the minimal model program gives us, is that with this definition of Higgs sheaf and with this definition of stability, we can pull back, we can compare stability downstairs and upstairs, and then if you work enough, you will find that this definition of Higgs sheaf actually gives us a meta-Ramanathan theorem. So this is now a theorem which I'm not going to prove. So with this definition, get a Ramanathan theorem for torsion-free Higgs sheaves on singular spaces. And the proof is use everything that minimal model theory gives you. On KLT spaces. For non-KLT spaces, actually, I don't know, and I'm mildly skeptical that such a thing will eventually work. Right. Now, let me indicate in a very simple case how this can be used to patch together a proof of this theorem, and then maybe use the last 10 minutes of the talk to explain where I think this whole theory goes and what we can learn from the proof and what can be done if you take the ideas of the proof and generalize them in the appropriate sense. So, where am I for? So, idea of proof for characterization of singular Ball quotients. So let me make one simplifying assumption right away. Assume with loss of generality, with a lot of loss of generality actually, that Kx is ample. So X already is the minimal, is the canonical model. So right, then we would like to show that X itself is now a singular Ball quotient. I assume that. I know this is a previous result of us. If you have any KLT space, projective or not, then there exists a quasi-étale cover, say x hat over x, such that the fundamental group of x hat and the fundamental group of its smooth locus, they're the same. This is not exactly true as stated. What we can prove only is that they're the same after profinite completion. And passing to this quasi-étale cover, so let's assume X already has this property. So we can assume without loss of generality X already has this property, and that means, well, if it weren't for the profinite completion, that would mean that any local system that I have on the smooth locus actually extends to a local system on X, right? Now, using Maltsev's theorem, finitely generated linear groups are residually finite. It's actually enough to have this result in order to get your extension of local systems. So any local system on X reg will extend to a local system that's defined in all of X. The hypothesis is that the profinite completion of X, pi1 of X reg, is the same as the profinite completion of pi1 of X. X is, so we are in the setting of this theorem, X has terminal singularities. KLT would suffice, but we are proving the theorem, so there's terminal singularities. If you weren't to sit in the last row, you could actually read this.
Well, someone has to sit here, no?
Yeah. Sure. Quasi-étale is étale except over the singularities, possibly. So unramified in codimension 1. Right. So then, now, look at the Higgs sheaf that I have been discussing a little while ago, namely omega 1x plus OX. This is so with its Higgs field. And then classically, you know that this Higgs sheaf, if X was a manifold, it was known by Enoki that this Higgs sheaf is actually stable. So in the singular case, you need a generalization of this, and this is due to Henri Genancia. So this is stable. Now, restrict to a general complete intersection surface, say S. S is a general complete intersection surface in my manifold X. However, because X has singularities only in a set of codimension 3, a general complete intersection surface will be contained in the smooth locus and will itself be smooth. So then by Meta-Ramanathan theorem, the restriction of this Higgs sheaf is a Higgs bundle on that smooth surface. And I look at E restricted to S and its endomorphism sheaf of E restricted to S. Now these are Higgs bundles on a smooth surface, so we are in the classical setting. This is stable by Meta-Ramanathan. This is semi-stable because it's a tensor power of stables. And then we, so this is stable by Meta-Ramanathan. This is semi-stable, and first Chern class here vanishes. Second Chern class vanishes because we're assuming equality here. So C1 is 0, C2 is 0 by assumption, and then we get a local system on S. So we have a representation pi1 of S into some general linear group. But then the Lefschetz theorem for homotopy groups in the singular setting, this is Goreski-McPherson, I think, says that this is the same as pi1 of X rag, because this is a general complete intersection surface, and we have the Lefschetz theorem. So we get a representation of pi1 of X rag, or if you wish, we get a local system on X rag. So we get a local system on X by get local system on X. And if x twiddle to x is a resolution, then Takayama has shown that the induced map between fundamental groups is actually an isomorphism. So pi 1 of x twiddle is pi 1 of x. So I get a local system on x twiddle. Aha. But now on x twiddle, this is now a manifold, I have the Correlate-Simpson correspondence. So Simpson says I get a Higgs bundle on x twiddle. So I start with my x. Inside my x, I have the surface S. I have a few singularities. I resolve the singularities. Here I have some x hat. And out of the initial data that I have constructed a Higgs bundle on x twiddle, which on x twiddle I know precisely what it is. Namely, it's the thing we started with. We have nothing done at x twiddle. Now you need to observe, and this is a step that takes some work, is this bundle comes from x and is and E. The bundle that we have constructed upstairs comes from x, and I will say in a second a word why these bundles come from x. But the point that I would like to make is what we see out of this is that E and E is actually a bundle. Now what is and E? E we know E is omega 1x plus OX. Now you take the endomorphisms of this, and then you find omega 1x as a direct summand. So a direct summand of a bundle is a bundle, right? So this means the tangent sheaf is locally free. That means our space was smooth to begin with. Okay, but then we can apply the classical Yale result. So this is like a brief overview of a possible proof in a singular case. Of course, maybe you find it much more interesting to directly construct the variation of Hodge structures on your singular space and talk about period maps in the singular setting. And this is what I would love to talk about today, but I can't. Instead, let me say a few words to where this proof actually goes and what we really have shown here if we invest the sufficient work. So one is this thing with the descent of the bundle. I have a bundle upstairs, now I claim it comes from downstairs without having explained why, right? So I should say something here. Let me put this a little into perspective. Personally, I never knew what a rational singularity was. I mean, I had seen the definition, but I never knew what it meant until it was explained to me. If you have your space X with rational singularities, let me draw that silly picture again. X now has rational singularities. You resolve this rational singularity, you get an exceptional divisor E. You look at the exponential sheaf sequence upstairs, you push it down, you use vanishing of R1 pi push forward structure sheaf upstairs, and then you will see a partial meaning of rational singularities. Namely, any line bundle upstairs that topologically looks as if it came from downstairs comes from downstairs holomorphically. So this is one, if you wish, trivial consequence of rational singularities, but I was quite excited when I learned this. Line bundles that topologically descend holomorphically. And what we show is that for KLT spaces, which are rational, by the way, so they have rational singularities, there's a stronger descent theorem that pertains not to line bundles but to vector bundles, and not to topological descent but numerical. Namely, what we prove, and I should acknowledge a little bit of help by Andreas Höring, by the way, what we prove is that if you have a space with the KLT singularities, we can do a little more general, but let's stick to KLT. You go to a resolution of singularities, and upstairs you have a vector bundle that numerically looks as if it comes from downstairs, then it descends holomorphically. And what do I mean by numerically looks as if it comes from downstairs? There's the notion of a numerical flatness that was introduced by Desmaillet, Peter, Nell, Schneider, I believe. It means that the bundle is Neff on the fibers and its dual is also Neff on the fibers. So this is maybe an interesting side remark that has its own pitch potential. So where to go from here for vector bundles on resolutions of KLT singularities. I can't say much about the proof. The idea of the proof is you have your desingularization map. You can assume that this pi actually is a run of the minimum model program. Then you want to descend your vector bundles. Vector bundles are hard to deal with, so you projectivize them. So here you have your P of E, you have your run of the minimum model program, and you want to, well, P of E prime run an analogous minimal model program for the projectivized vector bundles, and then it works, but it's some work. Okay, so this is what goes into this descent theorem. But now, if you have a KLT singularities, then Takayama has shown you that the fundamental group downstairs and upstairs is the same. We are showing that the vector bundles downstairs and upstairs are the same if they're like numerically flat or something. And then with a sufficient amount of work, you can probably see where this is headed. What we get out of this is a Corlett-Simpson correspondence for the singular space. We get a Corlett-Simpson correspondence for the singular space by, with sufficient work, this is many, many pages, relating it to the Corlett-Simpson correspondence on the smooth locus. But maybe the interesting thing is that our singular Corlett-Simpson correspondence, like the original one, is functorial in morphisms. And this is true for morphisms that end up in the singular locus. So, in 5 minutes, I'm not going to say anything about the proof. I just say I get a Corlett-Simpson. Bitte? But some accent someplace? On KLT spaces. So Higgs bundles correspond to local systems. But this is only half of the story. The other half of the story is on the singular space. As we have seen, there are two fundamental groups of interest. One is the fundamental group of the space, and one is the fundamental group of its smooth locus. And we have seen that the two are not the same, but we can compare them after going to quasi-étale covers, appropriate quasi-étale covers. Obviously, now you wonder about what about the smooth locus? And what we would like to say is we're seeing some new feature of singular spaces here. On a singular KLT space, there are two Colette-Simpson correspondences. One links local systems on X to Higgs bundles with appropriate semi-stability and Chern classes. And one links local system on X reg to Higgs bundles on the smooth locus, which have appropriate boundary behavior at the singularities. So they won't extend to Higgs bundles on X, they will extend to sheaves whose singularities are not so bad, and let me just stay there. So we get Simpson, Colette correspondence between local systems on X reg and Higgs bundles on X reg with good boundary behavior. So, and this is essentially what you can already see on the proof. In the proof, we have used our Higgs bundle in order to come up with a local system on X, which then extended to a local system on X reg via the second Colette-Simpson correspondence. That means that you get a Higgs sheaf on X reg with defined boundary behavior. And if the local system extends, then the Higgs sheaves also extends. Of course, the two Colette-Simpson correspondence here, they have optimal interplay. And because we started with a situation where local systems always extended, that meant that our Higgs sheaves extends to a bundle, and that was the whole point. So this is, I think, what we can learn from this proof. Now, how do you come up with such a result? I can't say more than a few words. The Simpson-Colette correspondence on quasi-projective spaces has been studied. There's a whole theory with many, many books written by Mochizuki. And what we can say, in a sense that I cannot quite make precise, is if you're not dealing with arbitrary KLT spaces, but if you're not dealing with arbitrary quasi-projective spaces, but quasi-projective spaces that are the smooth locus of a KLT space, then this Mochizuki theory simplifies to give you an honest equivalence of categories. This is essentially what I have to say. Bottom line is, what can we learn from there? Well, essentially that, with a grain of salt, pretty much all the theory of Nonabelian Hodge correspondences and variations of Hodge structures that come out of this, for singular spaces, they just work. What we can learn from this teaser application is maybe that if you're dealing with singular spaces, you might wonder whether uniformisation is actually the correct problem. Maybe the correct problem is quasi-étale uniformisation. We are learning that Chern class conditions can enforce quotient singularities. And we are learning that singular bulk quotients are objects that might be worth a study. So you could try and now study these spaces using the theory of automorphic forms. It's not so hard to see that, like regular bulk quotients, singular bulk quotients are Galois invariant. They are defined over number fields. But at the moment, I'm puzzled what would be the analog of Mostow rigidity. I don't know. And I guess my time is up. Thank you for your attention.